Here we have the integral of x times the square root of 2x minus 1 dx. We're going to solve this using two separate methods. First, we're going to go a traditional route, and we're going to let u be the part that's underneath the square root. So we're going to let u equal 2x minus 1. Now, the derivative du is just 2 dx. So here, I will be able to replace dx with 1/2 du if I divide by 2 or multiply by 1/2 on both sides. So I'll be able to replace my dx with 1/2 du. So let's make our current replacements. Let's start our change of variables. So what we're going to have at this point is the integral of, I'm going to leave this x alone for now. I'm going to replace 2x minus 1 underneath the square root with u. So I'm going to have the square root of u. And then dx gets replaced with 1/2 du. But the problem is this extra x. So in a standard change of variables, when I take the derivative of u, it's a multiple of any extra x related terms on the outside. But this x was not replaced with my du. So I have to perform a complete change of variables here. I need to somehow turn this x into something involving u. So what I'm going to do is rewrite my original equation. I'm going to solve it for x. So since it's linear here, I can solve for x. I can add the 1 and divide by 2. So this is going to become u plus 1 is equal to 2x, or u plus 1 over 2 is equal to x. And now I'm going to replace x with something involving u's. U plus 1 divided by 2. So now my integrand entirely involves u. So let's simplify it a little so we can start to integrate. So I have a 1/2 here and a 1/2 here. So I'm going to pull that out as 1/4. The integral of, I have u plus 1 times the square root of u, or u to the 1/2 du. So here, I'm going to have to distribute u to the 1/2 into this binomial so that I have terms that are added so that I can apply the power rule for integrals. So I'm going to have 1/4, the integral of u to the 3/2 plus u to the 1/2 du. If I distribute here and add those exponents. Now let's find the antiderivative of each term. So I'll have this 1/4 here on the outside of u to the 5/2, if I add 1 to 3/2, times the reciprocal 2/5, plus u to the 3/2, if I add 1 to 1/2, times 2/3, and then plus c. So now we will substitute our u back in, and we'll also at the same time distribute in the 1/4. So that's going to leave me with, let's see, 1/4 times 2/5. That's, if I divide 2 into 4, I'm going to have just 1/10. So I'm going to have 1 over 10, and then 2x minus 1 to the 5/2. And then here, if I distribute 1/4 times 2/3, again, the 2 divides into 4 2 times, so 2 times 3 on the bottom is 6. So I'll have plus 1/6 times the quantity 2x minus 1 to the 3/2 plus c. So this was one method of applying a U-substitution, or I think more appropriately, a change of variables. We changed all the x variables into u variables, so you could see each of those substitutions happening. Now let's try that same problem using a different method. This time we're going to let u be this entire square root piece. So u is the square root of 2x minus 1. Now instead of jumping straight to finding the derivative, we're actually going to square both sides. Since I have an equation, whatever I do to one side, as long as I do it to the other, like this, I'll have an equivalent equation. So I have u squared is equal to 2x minus 1. Now we'll take the derivative of both sides. So that will leave me with 2u du is equal to 2 dx. Or I can divide both sides by 2 and say that u du is equal to dx. All right, so how does that help me? Well, I'm still going to perform a change of variables here. I'm going to replace the dx with u du. So let me color code things a bit here. So let's say that this dx is going to get replaced with u du. So I have u du. And then the entire quantity, square root of 2x minus 1, gets replaced with just a u. But I still have left this x here. So I still have this x, and I can't mix u's and x's in the same integrand. So now let's go back and look at this second equation here. I can solve this second equation for x. I can isolate x to be in terms of u. So let's do that. Let's say u squared plus 1 is equal to 2x. Let's divide both sides by 2. So u squared plus 1 over 2 is equal to x. So we'll come back over here and substitute that in. So x is u squared plus 1 over 2. All right, so now let's see what we have. I'll pull out the 1/2, so I have 1/2 the integral of u squared plus 1 times u squared du, this u times u here. And that's 1/2 the integral of, I'm going to distribute in the u squared, so u to the 4th plus u squared du. And when I take the antiderivative here, I'll get u to the 5th over 5 plus u cubed over 3 plus c. And we'll do two things at once here. Distribute in the 1/2 and plug u back in, but u was the square root of 2x minus 1. So we'll have 1/10 and then the square root of 2x minus 1 to the 5th plus 1/6 the square root of 2x minus 1 to the 3rd plus c. And that is an equivalent answer to our previous one because I can rewrite the square root as 1/2. So this is 2x minus 1 to the 5/2 plus 1/6 the quantity 2x minus 1 to the 3/2 plus c. So just kind of showing some different options here for our change of variables and what we can choose with our u. I would say the benefit here is we were able to just deal with integer exponents throughout most of the problem. Now let's integrate x cubed all over the quantity x squared minus 1 to the 5th dx. So here we're going to let our u be x squared minus 1. And when we take the derivative, du, we're going to get 2x dx. Well, in the numerator, I have x cubed dx. So I will be able to rewrite one of the x's up here to things involving u. So if I divide by 2 or multiply by 1/2, I have 1/2 du is x dx. So I'll be able to rewrite one of these x's with the dx as 1/2 du, but I'm still going to have x squared left over. So let's kind of start to piece this together here. So I'm going to rewrite my original integral as x squared times x dx over the quantity x squared minus 1 to the 5th. So we're going to be able to rewrite x squared minus 1 as u. So my denominator will become u to the 5th. We will be able to rewrite x dx as du. So x dx will, be 1/2 du, 1/2 du. But we still have an x squared. Again, we cannot mix x's and u's in the integrand. I still have x squared. So we go back to the original equation relating u and x and realize we can solve for x squared if we add 1 to the other side. So u plus 1 is equal to x squared. And that will allow me to complete my change of variables. I'm going to rewrite x squared as u plus 1. So I now have u plus 1 times 1/2 du all over u to the 5th. Let's start to rewrite this. Let's pull out the 1/2, that constant multiple. I have, now we're going to split this up, u over u to the 5th plus 1 over u to the 5th du. So when I have one term on the bottom and terms on top being added, I want to split it up. Let's, from here, rewrite u over u to the 5th as u to the -4 plus u to the -5 du. And then we can find the antiderivative of each term here. So we're going to have 1/2 u to the -3 over -3 plus u to the -4 over -4 plus c. And now that we've taken the antiderivative, we can substitute our original u back in of x squared minus 1. I will also at the same time bring those quantities back down to the denominator to make those exponents positive and distribute the 1/2. So that's going to leave us with a final answer of -1 over 6 times x squared minus 1 cubed minus 1 over 8 x squared minus 1 to the 4th plus c. So I distributed the 1/2 in and brought that down to the bottom while plugging in x squared minus 1.